Still need some vice versa. No, it's okay. It should be. Okay, working.
So with the partition, we define the itinerary on the set of itineraries. So the sequence is shift up. We just erase the first or the zero of the string. Okay, so we say that itinerary is bounded as if the sequence is just bounded. The most important definition on this slide is exponentially bounded itinerary. This definition, it means that the sequence of integers of the itinerary grows at not faster than iteration of such function. So the iteration of exponential function times some constant. And this is important definition for us because we will see probably on the next slide. Now, definition: escaping point is the point of the plane which escapes to infinity with iterations of f.
And assume that lambda is close to zero. I just
no, so this one you do not assume anything about the lambda, just not equal to zero in general case. But now there are only some definitions. We will assume something about lambda later. A tail of a hair, there will be a definition of a hair also. A tail of a hair with given itinerary, it's an objective curve on the convex plane, satisfying the following condition. Each point on the curve is an escaping point. So every point individually will escape. Every point has itinerary S, in itinerary S. So it escapes with itinerary, and the curve itself, there is a tail. It goes, this tail goes to the right, to plus infinity, the real, to the right side of the plane. The real value goes. Okay, and now we'll see why the definition of exponentially bounded itineraries is important, because it's important to say that I presented you the theorem as theorem of Schleicher-Zimmer, but it's because they generalize it for lambdas, every lambda different than zero, but a lot of results, partial results, were proved earlier, not by Schleicher-Zimmer, for example, Devaney and Krieg.
In particular, this theorem was proved by Devaney and Krieg with some additional assumption about
yes. So Schleicher-Zimmer, and I will say probably in the next slide something about the previous than this theorems. So first of all, we define the set of C which shares itinerary. There is itinerary, and we take all C with this itinerary, and there is lambda S. And this set is not empty even only if S is exponentially bounded. And for example, Devaney and Krieg, it was at least 20 years earlier than 2003, proves the same result, but for special case, I think real lambda.
So you assume that every point in the pair escapes from the
So
no, not yet.
Now we don't have hairs yet, but
I will tell you what I have in mind. Some pairs, including the end, escape from the for some, we don't know anything. They will tell us what happens.
So
and the open part of the hairs.
Yes. So thank you for the remark, because when I say hair, I usually I mean the open part of the hair. So I treat endpoints separately. Sometimes the endpoint is escaping, sometimes it's not. Sometimes there is no end. 1. But it's not only for exponentially bounded itinerary, it's not only non-empty. For every exponentially bounded itinerary S, there is a tail of a hair. So inside the lambda S, there is a curve of points which escapes to infinity. So all escape points with given itinerary form a curve inside lambda S. And we know that what happens with the curve far to the right. The question will be what happens to the curve on the second. And here is a classification of all escaping points. So there is not only tail of a hair, all escaping points form a curve. We call it a hair. And the construction is follows from the relating f lambda with by some functional equation with f, big F, which is e to the t minus 1, the function on real numbers. And every escaping point with given itinerary has to be the element of the unique hair or a landing point, endpoint of the unique hair, or there is a special case that it may maps after finitely many iteration on the hair related to the asymptotic value 0, but we'll not focus on this case. It's related to itineraries which ends with the sequence of zeros. Because the asymptotic value 0 has itinerary of all zeros. So the most important thing from the slide is that all escaping points forms curves.
You said asymptotic value has itinerary consists of zeros only, but this is for real lambdas only. Because otherwise.
Okay, so
That's why
it's not
quite stable like this. So after it lands on the hub, single value. Because in the general case, this is more complicated.
Okay, so as I said before, the existence of the hairs was shown previously earlier by Devely and Kry for some special case. They just take f lambda with lambda from 0 to 1 over e, and they discover the quite beautiful structure of the Julia set of the number. I don't know if they call it or this structure is called quantum bouquet. Okay, this is the image, but this image is not perfect because what is important, we have a lot of uncountably many curves. All these regions are in fact curves which goes from here and to the right. So they are just so densely packed that we can draw the image properly.
Yeah, you should have asked. I have a slightly better picture.
Okay. And the small remark is that the structure is called quantum bouquet, but what is the structure? And Arts over Stiegen proved that for at least lambda between 0 and 1 over e is homomorphic to such model, straight brush, which is just that of lines, half lines. So we have plane. P is the set of rational number, and at some height we have such half lines. There is a lot of these lines because the three conditions for straight brush are as follows. At every height there is a beginning of the hair of the. There is a beginning, and we go to the right. Density for every height and for every height at which there is a hair, we have a sequence of hairs from above and from below, such that the endpoints goes to the and from below and from above separate. And this set has to be closed in the plane. And Hausdorff can prove that the counter K is in fact homomorphic to the straight brush. So this is the model for the topology counter for the Julia of F lambda for such lambda. And it was generalized. For example, there is a theorem of Rempe that for general lambda, if there is an attracting or periodic orbit, then every, in fact, it's equivalent. Then every curve of F lambda lengths, so there is a point every curve, and every point of the Julia set is on the curve or is the endpoint. So the Julia set is the set of landing curves. And in fact, this theorem is with some assumptions true even for wider class of functions. If you assume that F is from class B, we will not talk about it, but there is some class. If you assume that the function is from this class with bounded, class B is the class of function with bounded singular values, set of singular values. There should be an assumption of finite order, and I'm not sure is it enough or maybe something else. This is theorem of Balansky. Then the Julia set of such function from this class B is also counted. On the other hand, so we show the case when Julia set is set of densely packed curves, but sometimes the Julia set of F lambda is the whole complex plane. For example, F1. If we take lambda equals 1, then the Julia set is whole complex plane. And in general, if the 0 goes to the infinity, 0 is a escaping point, then we are sure that the Julia set is the whole complex plane. But this is not all the cases. For example, for lambda 2 pi I, also we have Julia set as whole complex plane, but the 0, the trajectory of 0 is quite simple. 0 goes to the 2 pi I, and 2 pi I is a fixed point. It's a repelling fixed point, and if lambda is started as a value eventually lands on the repelling periodic orbit, then also Julia set is C.
Mechanism is simple. If Julia set is not the whole plane, then there should be some normality domains. It should be served by trajectory of critical. And here trajectory of
so it's important to mention that
zero is serve anything because escape or eventually.
0 is the only singular values asymptotic. Zero value asymptotic value of F.
Cannot play its role as serving some base. But Mishurevich didn't use it.
The proof of Mishurevich is without any big components.
Something right.
Just
estimate and then we do this.
So in general, if you take the set of escaping, I didn't define it, but E of function is a set of escaping points. If you close it, then it's the Julia set. And it's not, I defined it, sorry. And it's not only true for exponential function, it's again true for some class of function, again, class B, for example. Yes, I believe this is the result of, but there was some previous result for some smaller class of functions. I think it's again Devini with, I don't remember, it's Devini with the sum. Okay, but we want to talk mainly about the Hausdorff dimension. So briefly about the Hausdorff dimension of the whole Julia set, because our goal is to talk about the Hausdorff dimension of the, we choose the itinerary, we look at the specific set lambda S, and we want to tell something about the Hausdorff dimension. Firstly, shortly about the Hausdorff dimension of Julia set. If lambda is not equal to 0, Macmillan proved that the Hausdorff dimension of Julia set is 2. So if Julia set is complex plane, then it's obviously 2. But for this example with quantum depth, it's also 2. But with in this case, when we have hairs, the area is 0. And then there is a theorem of Karpińska, which said that for such lambdas, this Hausdorff dimension equals 2 is concentrated on the endpoints, not on the pairs, on the endpoints of hairs. So all endpoints have the Hausdorff dimension 2. And without the endpoints, the Hausdorff dimension of the whole Julia set, so hairs without the endpoints, union of all hairs, is equal to 1. So the smallest value for set of hairs. And again, Schleicher-Reisman proof the same. There should be. This is for F lambda.
This is called Karpińska paradox.
Yes, this is called Karpińska paradox. And here the union of all hairs for F lambda general case. Without the endpoints has Hausdorff dimension 1, even when lambda is not from 0 to 100. This is the same result, just very general. Okay. So now we jump to slowly to the considering a special one hair. If we have such parameterization, then we know what happens close to this end. The curve goes to the right. So we are curious what happens close to the left end. So we define the accumulation set of as a set of all possible limits when it goes to 0. We go to the 0. We look at the set of all possible limits, and this is the accumulation set. And sometimes it's the only one point when the hairs lengths. So, for example, for F lambda with lambda between 0 and 1, 1 sorry, all hair lengths. So the accumulation set of all hairs is some specific one, someone for every hair there is 1. And so this is the image of a landing hair, but sometimes the hair do not length. And we ask what is the accumulation set. So we are interested in this. We are interested. So there are some conditions on landing hairs. So I will talk about it fast because we are interested in hairs which do not land. There is a classification of itineraries, which says that F is fast if it satisfies such conditions. So it says that for all sufficiently large n, if we start our itinerary from n, then there is entry which contradicts the assumption, contradicts the condition on the exponentially bounded itinerary. So the opposite slow itineraries are such that there is a sequence of n's, such as if we start itinerary from this point, it's exponentially bounded with the same a and x.
What is denoted by capital F?
F is just e to the t minus 1. Is defined by the formula. And for fast itineraries, like I've seen it proof that all hairs with this itinerary lengths, and this point is an escaping point. But this is not all cases when hair lengths. For example, for slow itineraries, hair also may lengths. For example, when there is no 0 or finitely many zeros in at least for real lambda, positive real lambda, then the hair is not fast, hairs are slow, but it lengths. So we see that if we consider real lambda, and we want to investigate the non-landing hairs, there has to be a lot of zeros and infinitely zeros, but this is still not sufficient for her to not land. And again, this is generalization of some previous result. For example, for bounded itineraries without the entry 0, there is a similar result of such 6 outwards. Okay, so a definition: a continuum is a non-compact connected space, it's a pathological continuum, and indecomposable continuum is a continuum that cannot be represented as the union of two proper subcontinua.
Could you show again the previous slide?
Yes.
The slide that's in.
So in this case, the generalization is that they do not assume
the central strip is
Disallowed.
yes, the central strip
is not escapable, different.
yes, or correlation. This is that it's allowed, but finitely many times.
Fine. Times. Then there might be complicated.
Yes. Okay. So deviant, there are set of theorems which says that for such itinerary, the accumulation set is in fact complicated. It's in the indecomposable continuum, and there are several constructions. One by Devaney for itinerary of all zeros, but I present you the theorem of Devaney and Kharkiv for non-specific itinerary. The theorem is as follows: we have f lambda. Lambda is greater than 1 over e, because if it's smaller and real, then we know that for times. So the complex plane, the Julia set is the whole complex plane, but we have hairs from escape. Okay, so T0, T1, and so on is a sequence of finite blocks. So every Tk is a block of integers. So we have given sequence of blocks of integers. And this sequence composed from all these blocks has to be bounded, not exponentially bounded, has to be bounded. This is the assumption in this theorem. And the theorem says that with such blocks, you can create an itinerary by inserting zeros between these blocks, such that the accumulation set, which is in complex in Riemann's field accumulation set, we also count infinity if there is a sequence from infinity, but there always is a sequence because we have a hair, which is the closure of the hair with infinity, which is the whole set lambda s. It's an indecomposable continuum in the Riemann's field. And in fact, here this sequence of zero it follows from the proofs. Has to be the length of this blocks of zeros grows with every block. So the theorem says that we can insert some blocks of zeros, and such itinerary generates the indecomposable continuum as the set lambda s.
So the whole hair is contained also.
Yes, the whole hair is
Not on the end, but the whole hair.
We looked at the specific hair, and this hair have accumulation sets, which is the whole lambda s, and it's complicated.
Because I could say that the endpoint is replaced by
yes, the endpoint is
but in fact this continuum also contains the hair.
Yeah, the accumulation set contains the hair itself. So
that does this assumption say that these integers are uniformly bounded?
Yes, the assumption says that. The assumptions are that at the end, this itinerary has to be bounded.
So the NQs are uniformly bounded in this construction.
No. The question is about the ends. Sorry. So
these are bounded
And if
In
you
the values, but not necessarily in the length.
Yes, yes.
Mhm.
T's are bound in the values
Mhm.
by common constant,
But then,
but length can be arbitrary long.
but take a bounded sequence of numbers and then you can
Yes, so
separation with zeros in such a way that this builds a
yes, so in fact we take the one bounded sequence of values and we choose some places where we want to insert zeros, and we are guaranteed that if the blocks of zeros in this spot are large enough, then we have an indecomposable concept. And I managed to prove this similar theorem, but there is no assumption that the blocks of zeros are bounded. And again, all and other assumptions are the same without assumption of boundness. And again, the result is if you insert blocks of zeros, if they are large enough, long enough, then the set lambda s is an indecomposable continuum. They must be together. And this theorem, the Devaney-Halke theorem, and some other theorems which proves that the accumulation of hair is complicated, uses the theorem of Curry, which says that the idea is that if the hair accumulates on itself, in the curve, but for us, our curves, accumulates on itself, then with some other assumptions, the accumulation set is the indecomposable continuum. Accumulating on itself means that the accumulation set contains hair. So if we have hair and we choose any point on the hair, and we look at the neighborhood, there is infinitely many parts of the curves, later parts of the curves in the sequence of points. Okay, so
Experience was this last year. Is it for each class? Is it for exponential?
this is for exponential. The exponential with lambda greater than real, greater than lambda.
Oh, so you mean the last? You mean which last theorem?
Okay, so this is for
This one.
okay, so the whole presentation is about the exponential function. This theorem is about the real lambda greater than one.
It was purely pathological.
yes,
Yeah.
this was like
So this is purely topological theorem. It says about the curves, but we use this because we have first and we use the theorem. So this is not about there is no function. Okay, so at this point we want to know that for some there is a setup for which the lambda s is complicated because. Okay, so now we go to the Hausdorff dimension of specific lambda s, and I will talk about something about the result of Łukasz Paweł's Anna Stunik, because it's introduction for the, let's say, new result. So we need some definitions. We define a supergrowing parameter lambda. This is a set of parameters for which zero has some special trajectory. It escapes to infinity, but fast. It means that if alpha is the real value of the alpha n is the real value of the nth iteration of zero, then the next lambda alpha n plus one should be at least some constant times e to the previous one, e to the lambda n. Then obviously zero escapes, but it says that zero escapes, let's say, fast. Okay, and the next definition is the fin set. We take the W, which is a closed set, and we define we cut W at the x equals r and minus r, we measure the diameters of these cuts. And the small w of r is the maximum, these two values. And we say that w is thin if there is a constant such that this condition is satisfied. It means that whole set w is in some column. And the second condition tells us about how fast the width of the w can grow. And this. So, for example, horizontal strip is obviously thin, but the cone itself is not thin. It's somewhere between. And the theorem is as follows: we take the super growing parameter and w, which is a thin set, and define the set lambda w, similar to the lambda s, but we consider all z's for all iterations of z's stays in w. So this for which the whole orbit is in w. And ym is just the union of right half plane from m to the right and left half plane from minus m to left. And then the result is that the limit, if you take the m goes to infinity, of Hausdorff dimension of the intersection is at most 1. And for us, what's interesting is the rather corollary from this theorem, such that if we consider unbounded trajectories inside the lambda w, then the Hausdorff dimension of such a set is at most 1. And the corollary follows from we just if the z has unbounded trajectory, we wait for a moment it's far to the right and far to the left, and then we can conclude with this result. Okay. And with such theorem of Deming-Harke, we have such corollary. Deming-Harke proved that for bounded itineraries, the set of points with bounded orbit is small. And by small, I mean there is exactly one point with bounded orbit. If we take the itinerary S bounded, then the set lambda S has one point with bounded orbit, and all other points have unbounded orbit. And therefore, we can use the previous result and the corollary from the previous result and state that if we take the bounded itinerary, there is an assumption that S is bounded and do not end in all zeros. Because if it's end in all zeros, there are two fixed points. Let's take this itinerary 0, 0, 0, and so on.
Lambda S was limit point. What was lambda S?
Lambda S is the set of all points Z with itinerary S. So it's a curve, but it's more. It's
but not ends.
No. Lambda S. We take all points with itinerary, no matter what is the dynamics. It's not end. So there is an assumption that ends in all zeros, and it's related to the third case of classification by Zimmer. It doesn't matter for us. So we take the S bound and do not end in all
something like
zeros.
this was for just all pairs for exponent lambda.
Once again,
Something like this was. I think that this is related with the theorem that has the dimension of union of pairs for special cases of lambda times x.
But
It's one.
we're not talking pairs, we're talking about closure
Well, that was my question. So lambda is a closure. What is lambda?
Lambda is the set of all points within an itinerary, which contains. We are sure that it contains the closure of the hair. But usually it's the closure.
Usually for lambda times s it's not. Closure is just 1 point. So
no, closure
with her.
Closure with a standard closure, closure of the hair contains the hair itself.
This is special. This is special because for lambda times x, it is not so because limit of the hair is just 1 point.
Yes, but closure contains the set itself for any set.
Topological
closure. Not accumulation set.
Topological closure of any hair contains.
Topological closure of any set contains the set itself.
But if it is just unique hair.
Yes.
Then the dimension is trivially 1. It's a curve.
Okay, but I had in mind union for hairs.
Yes. Okay. So
then,
okay.
Then I had the impression that the dimension of union.
Yes. Yes.
This one is related to.
Yes. So yes, this is true. So if we talk about the union, then.
But we will discuss the individual.
Yes, we discussed the union earlier. Now we discuss the individual hair.
This doesn't look paradoxical.
Yes, so this doesn't look paradoxical, but if we focus on landing hairs, it's not paradoxical at all. But if we focus on the indecomposable ones, it may be not obvious. In fact,
it looks like in Smith's horseshoe, you take the unstable global manifold and you obtain, as a closure, you obtain an indecomposable continuum as well. It is locally like Cartesian product of line and Cantor set of positive dimensions.
So
maybe here structures.
If we focus on the specific itinerary, even if we take the hairs for which there is a complicated set, if we measure the Hausdorff dimension, it's 1, so the smallest possible value because we have curve inside. So in particular, the indecomposable continuum of the Riemann has dimension 1. This is the smallest.
And actually, I think I don't know if this is true. If there's a hope for this, because so if you want to prove that that the union of all hairs has half the dimension of 1. So the difference obviously between this and the previous situation, then we had the bucket which had zero area, and now we have the full plane which has full area. So now hoping that the whole area is given by the endpoint, but the accumulation set seems even more paradoxical than the previous one. I'm not sure if there's any hope of achieving that.
Perhaps in the orbit of 0, so it's small. How
It's not an omega limit set. So it's closure.
The omega limit
of 0, so it is a small discrete set.
So I'm not sure what.
Wait. So the dynamics is very simple. The topology it may be very
But
complicated.
there is no closure. Orbit of 0 is just one orbit.
But that's the omega limit set.
Omega limit sets are either, so it means omega limit set is very small. Isolated. And my question is, so how corollary is related to the theory?
Okay, so the corollary is related that there is this part is not important. The important part there is unique point, 1 point. So we can forget that if we measure the Hausdorff dimension, we can forget about 1 point, and we use
so
the corollary
is about
bounded point.
Yes, but previous theorem. The previous theorem.
Yes, so this is the sequence of corollaries. So we have this corollary from this theorem. Then if we add this theorem that there is 1 point, then we have this theorem.
Okay, so about this lambda bigger than 1 over smaller.
Okay, so and some similar result may be obtained for again unbounded itineraries. But by similar, I mean that there is some kind of special bond, but we need some assumptions on the itinerary because, as I said earlier, for some unbounded itineraries, fast itineraries, the one candidate for a special bond is not special; it escapes also. So if we assume something, and the assumption is the same as the previous theorem, we just insert block of zeros between some blocks. If we did these blocks T0, T1, the itinerary created from without blocks of zeros, only from T blocks, may be unbounded, even not exponentially bounded. But we do everything with inserting blocks of zeros, we create some itinerary, and for this itinerary there is a special point, and the omega unit set of this point, unit is the omega unit set of Z contains Q plus or Q minus, which are two repelling fixed points in P0. P0 is the zero street, the central street.
So Q, so there are 2 points. One is on the top upper half,
yes,
one from the lower.
Lower. But the length of the blocks of zeros has to be has to grow sufficiently fast. And for all other points, the length is the same. If we at least look at the limits, the same as in the Riemann theorem for bounded itineraries. It's orbit of 0 and infinity for points not on the hair, and obviously infinity for points on the hair. Okay, so if you want to prove something about the Hausdorff dimension of points, and with this theorem, it can be shown again that the Hausdorff dimension of lambda s for such s is 1, and it's on. We only need to prove that if we take all z's without this special point. So all z's from this case. Then at some time there's an iteration that these points will land in the some thin set, and the whole orbit from that time is still in this thin set, but this thin set has to be common for all points. So there is a common thin set. We need to prove this that all points eventually will stay in this thin set, and it can be proved for such itineraries. The lengths of blocks are sufficiently large. So in particular, the Hausdorff dimension of the composite continua created from such itineraries are again, given that the itinerary is unbounded, it is 1 again. But this is only the remark. The theorem I want to tell about today is the work in progress with Asia Kowaczewska and Łukasz Pawelec.
It's not work in progress, it's publication in progress. Okay, not publication.
Technically in progress. In fact, I consider it as almost done, but it's not done.
How many papers?
It should be on archive in June.
Is it submitted?
No, it's not submitted. No, like we are like okay, that's publication.
So
To a final economic work.
so it is true that it's in progress. So for simplicity, we consider a specific one specific map F1. So lambda equals 1. So F equals e to the c. And we prove that for every exponentially bounded itinerary S, so for which there is something, for every other, the lambda S is empty. We have in the Hausdorff dimension of lambda S, it is equal to 1. So no matter what is lambda S, is it the hair with an endpoint, is it indecomposable continuum, or is it something else? Maybe there is something else. we don't know, I think, whether the indecomposable are only possible types of accumulation set different than landing pairs.
Well, it is known that if you take lambda equal to 2 pi I, then you can get different topological sets.
Yes, it is not that for lambda 2 pi I, there are some bounded indecomposable continua, which is the work of some, I don't remember the names, for sure there are Chinese names. Fu and Chan. There is also a work of Delaney, Hark, and Rocha, if I correctly wrote.
I think Rocha, yes.
Okay, that there is an indecomposable continua which is constructed as the accumulation set of two hairs, which accumulates on itself and on the second hair, something like that. But no matter what is the structure of lambda S, you can prove that Hausdorff dimension is 1, which is again the smallest possible value, because there is a curve inside always for a function matrix. So we know that the dimension is at least 1. We want to bound the dimension from above. So for lambda S, we want to construct a family of coverings. So Fn is the covering. We have coverings for F to N, so we have a family of coverings. We cover only the unbounded part of the lambda S, so the points with unbounded itineraries, because again, if the itinerary is bounded, then there is one point. If itinerary is unbounded, then in fact every point in lambda S has unbounded itinerary, because the itinerary is unbounded. But we cover both cases together with one proof. So we construct the covering with, if the n grows, then we want for the diameter of the covering to be smaller and smaller, closer to 0. And okay, we start with some n, but n is like some parameter. Given n, we have a lambda. We want to lambda be closer and closer to 0 if the n grows. And we want to bound such a sum with some constant, no matter what constant, but this constant must be the same for all n. And then from that, if this is true, it follows that the Hausdorff dimension is at most 1 plus delta. So if it goes to the n to infinity, and in fact lambda goes to 0 with n to infinity, then the Hausdorff dimension is at most 1. It's 1. So repeating the above construction to larger m, hence the proof. So the simple definition is the R, which is a rectangle. K gives the left and right boundaries, start with the real value with K and ends at K plus 1. And the bottom and top boundary is given by this n, Q is the upper index, Q is the lower, which is okay. PM is the strip between here lambda is 1, so argument lambda is 0, so PM is between 2n minus and plus 1. So we have a rectangle, K plus 1, 2n minus 1 pi, and 2n plus 1. Okay, so I will show the idea behind the constructing of the first level covering. So we, as I said, we construct Fn, the family of n, but the idea can be shown only by showing the construction of the first level covering. We construct the first level covering based on the based on the zero level covering, which is very easy. And then after that, we construct the n+1 level covering based on the nth level covering. By these constructions, the idea is the same as we construct the first from the zero. So I will show the construction of the first level cover. So so obviously the lambda is inside the strip. So if we take all rectangles, then it's covering, and we call it the zero level covering. And based on that, we want to create the first. And we do it separately for the right, left, and the middle part. So with n, we divide the plane on the right part, which is to the right from the vertical line given by n, left part, which is to the left from the minus n, vertical, and the middle part, which is between. And we start with R, which is the easiest case, then we do the L, and then M. So before I start, I would say that the construction for R, which is quite easy, and it's nothing new. It was done previously. You can see it, for example, in paper of Radosław. The construction of L was also shown earlier by Radosław. The new part is the construction of N. But I will tell about construction of everything. So we start with the rectangle, which is to the right from the N, R with some indexes. We look at the image, which is M is big, then big annulus, and we look at the elements of F0 covering, which intersects of such streets. And we look at it at the specific height, because if we take the image, then we have to look at the height S1. S1 is S0 is the first entry of itinerary, S1 second. And we take the three images, and we end up with some sets inside R, and we do it for every rectangle to the right from M. And the number of elements is constant times e to the k, where k is index, because the size of these circles is proportional to the k. And diameters of these elements is proportional to the e to the minus k, because f prime is equal to f for exponential function. So if we start with real value greater than k, then this radius is e to the k. It's in the radius, so the derivative is at least e to the k. So if you go back, then the derivative is at most e to the minus k. So if we calculate such sum for only R inside the given R, then we end up with some constant time e to the minus k delta, because we have e to the k times e to the minus k with some constants, with the 1 plus delta. So what's left is this one. And with that, we can, this is the geometric series, we can sum it to some constant. Here is 1, but well, it should be just a constant. The left part is more complicated. But again, we start with the rectangle, which is to the left from minus n. We create the some covering inside this rectangle, and we do this for all rectangles which are to the left.
If I may make one comment, so because this picture might be slightly misleading. So whenever we intersect this horizontal strip with the annulus, we can get those rectangles on the right, on the left, or in the middle. So they should be well read because by Radek's picture they seem to be on the right, but obviously can be on the left, or they can be like full. It could be like a long spot of the strip.
Can be like this. Can be also like this. So we are interested only in this part.
We still have very counts on the number of those rectangles, but it's like.
But in this construction, we just assume that we do not assume. We just take the larger possible value, which is the size of the. It can go also.
They are just made close to 0.
Annoyingly.
So from the left part, we take again a rectangle. So here K is greater than n plus 1, and we consider R minus K. So the K is the positive part. And fortunately, if we start with some point set far to the left, we know something about the at least few iterations, next few iterations of this point or set, because the far left half plane maps onto the ball center at 0. The bigger we send, the smaller we send. And if we are close to the 0, then for some time we should be close to the next images of zeros. 0, 1, 3, and so on. The closer we are, this journey is longer. Okay, so we start with this set. We map here. Then the first image is the here not so small, but we figure out the small annulus which center at 0, and then this set before might is like topological ring, and we wait for this set to be not so small. For us, not so small is that this distance is greater equal to P over 6. It could be different value, but in some calculation, we cannot take any value, but there are some. There is a set of possible values for which it works. Okay, so K is in fact time from here to the time we are not so small. So from this point to TK plus 1. Okay, and we consider big F, and now I see that this is the same letter. Now we forget about the F. We forget about the F equals e to the t minus 1. Here F is just the symbol for the map we want to pull back, and for left part it's decomposition. And the set, so we wait for our set is like this. We wait for this moment, and we can prove that this time is so big that we are far. We end. This set is to the right from K. If we start with minus K here, we end to the right from K. So, and if K is bigger than N, it's also to the right from N. And our R1, already constructed R1 R1 covering lives here. So maybe we can pull back this set. And here we do not pull back rectangles from F0. We pull back already created sets from R1. Because we are to the right from, you can calculate it, we are to the right from M. It may differ from the idea is the same, it may differ in some details.
The original covering?
Now the covering F0, we pull back already created R1 with proper means this one, the shift with pk plus 1 over s. We pull back with F, big F, elements of R1 covering for some itinerary. It's such that the intersection is non-empty. And here, in fact, we do not have any problem with some injectivity. We need to count the number of elements, and we need to check whether the derivative is big in this direction, so small in this direction. So that
because the derivative is very small at the first iterate, and then
I need a new picture. So use M. This F of R. And we have some rectangles here. We do not pull back rectangles, we pull back sets which are inside. And these rectangles are indexed by L. So if you look at the specific rectangle RL, but the intersection is empty, then there is e to the L times some constant elements of these small circles. We calculated already with covering of R. Okay. And the number of rectangles is proportional to the diameter of this set FR. So we somehow know how many sets we pull up. And what about the derivative? So inside given RL, the derivative is e to the minus L times some constants. So if we want to calculate this sum, we start with the R, K. So this sum on the left is something like this. We sum over all rectangles, so we sum over L. And inside every rectangle, we have e to the L number of elements, but the derivative is at most, we have okay, so that diameters of all elements here is e to the minus L, but we pull back with some function. So what we know about the derivative of this function? So we know it's we can prove that the distortion from here to here is bounded. So the derivative is proportional to the 1 over the diameter of the set. So we have 1 over with some constants, the diameter of FR e to the minus L. This is to the 1 plus that, and this is the structure of the sum. So so what is left from e to the L inside sum is e to the minus L delta. We have also 1 over diameter of F of R, 1 plus delta. And now we say sum over the number of L's is about is proportional to the diameter of R. So we have okay. So before that, L is at least K. We can put that. If we start with RK, we end to the right from not the M to the right from K. So we have K here. So we have diameter fr times 1 over diameter of fr to the power of 1 plus delta. So we end with minus delta times e to the minus k delta. E to the minus delta is this part, but fr is the first f. Tk was defined in such a way that fr is the first set with not so small diameter, so 1 over is not so big, so it's the constant.
But F was PK plus 1.
Yes, f is tk plus 1.
No, that's just a
But so tk was defined from the not from the left, it was from the neighborhood of 0.
Okay.
So in fact, f
No.
of r, which is tk plus 1, is the set we ends up is the first set which is greater the diameter.
Okay, so not extremely big.
It's not the it's before being extremely big. It's the first time we are not so small, and the next step is we are extremely big, but we are not going to the next step. We pull back from this state not so big. We are not so not extremely.
Okay, so tk plus 1 means that first we go from the left to the neighborhood of 0 and then apply pk iterates for.
Yes.
Okay. And
So we go from r to the neighborhood of 0 with f, and then tk times. So we have f. And we have a similar estimations for the right side. Okay, so there is a new part. So now we want to do very similar thing as for the left part, but in the middle part, the rectangles are not special, not so special as in the right and the left. So we need to define new sets for which we will pull back again the elements of as R1 for some let's see some magnetics. So we are here and we define the escaping time. So if we are here and our point has unbounded trajectory, it has to be here at some time. For unbounded arrays, this time is common for all points. For not for bounded, again we forget about this one square point. It's not common, but it doesn't matter for us. We do not assume that it's common or not. We assume we use fact that there is a time for every z. There is a time that this z is here to the right from that. And this time for every z is tau tau n. And we define from the to the left, and we define the set E. The bottom index is K, which tells us what is the escaping time. We find E K, but we also want to have given itinerary. So EK is a set of all points with escaping time K. And the first K entries of itinerary of point inside K is given by this sequence. So we want to control the itinerary. So this set is a set which exactly at the first time we are far from M is K, and we to that time we have itinerary given by the 0 and 1 and so on. So this is the final sequence. And the idea is to pull back. We are to the right from M, so maybe we can. The answer is that yes. Okay. We want to pull back with this function, which is f. For every ek, we have fk, which is, and the image of fk of ek is to the right from M. We want to pull back with fk. And
I'm going to be horrible and make one more comment to simplify this slightly. So we, in the middle part, we look at the how many steps exactly do we need to leave to the right of n, and then there's all annoying notations because first we need to keep to the itinerary, then we need to shift the itinerary correctly when we are going to pull back. So the shifting map is beta, and we have to keep the itineraries on.
no. The beta is just notation. Is the first beta of SK is the first k entries of S. So this is the on the notation.
Annoying notation because we have
We need this notation,
keep the sequence.
but it's annoying. The notation is part of
So there are as many betas as finite sequences of length k. Many.
So the image here is that we have EK, then in the next step, the image with one F is inside
But shifted sequence now.
EK minus one, but beta of K minus one, but of sigma of S. So this is F, and it repeats and then repeats. Okay. And what's worth noting is that this is the first time we are to the right from n. So if we leave this part, it must happen to this region, not some far away. This region is between this line M and the circle with radius e to the n. Okay, so we want to pull back as to the left, as in the left part. We want to pull back these elements back to the set E, some indexes. So there are some questions. Is it possible? Is it derivative? Whether we have the proper estimate on the derivative. So the first question is there a proper estimate on the derivative of f? We take the EK with, we set K and we fix K and we consider Fk. Is it the derivative okay for us? And it is. We do it as follows. So we take eta, which is 1.1. It's some constant. It must be constant close to 1. It could be 1.0. In some part, we would use the specific value, but it,
1.1.
it doesn't matter so much.
Geometric series we convert. I'm sorry. And
We need some. Yeah.
we need any constant. Well, no, 2 would be too much.
Yeah,
But
2 is too much. 1 is low. So, and the first result is, before you read this, the first result is, the idea is that if we are here, and after k iteration we are here, the derivative is at least lambda to the k. But there is a small issue that it's not always k, it could be the k plus 1 iteration or k plus 2. But it's just a small adjustment in the proof. This 1 or 2 follows from the small adjustment in the proof. The idea behind the proof is that we want to prove that f being on the k, it at least lambda eta, sorry, to the k. And we do it by considering 3 parts of the middle part. So we have minus m, and in this middle part we distinguish left, middle, and right again. But now we have some specific values, and that's why in our proof lambda equals 1. It's not so easy. It's not so easy, at least that moment, to generalize it for other lambdas.
well, it's definitely doable to generalize, but the proof is kind of subtle in the moment. So try to No,
Wait,
no, we didn't use lambda equal to 1 at any point. Here I kind of made some calculations, but the formulas start to be much too complicated for my liking. So it should be doable for any lambda bigger than 1, for example. But you have to be slightly more careful. And it's like there's still plenty of problems with those itineraries, and we decided against doing this generally.
Okay, so these lines are spots. We have k iterations, and we want to for our derivative to be eta at the end, at least eta to the k. So let's suppose that we are here at some time before the k we are here. Then here is to write log of ln of eta. So in one step we have the derivative at least eta. So this is the easiest part. So if we are here, and that time we are to the right, we have eta. And this is the move. Okay. If we are in the middle, then there is a direct calculation that in 4 steps, exactly 4 steps, it could be less, but in 4 steps, we are sure that we have, at the individual step, the derivative may not be big enough, but if we take the 4 steps, the derivative is at least eta to the 4th. So we have a block that here is eta to the 4th, and we just write the formula explicitly. So we need, if we are here, we need modulus of fz times the modulus of f to the second iteration of c after 4 iterations to be greater than eta to the k. And the formula, if you write it down, is terrible. But fortunately, if we take the log, we have the real values of these quantities, and we sum these values. And fortunately, we can see a harmonic function defined of some bounded set. So we need to check whether the estimate is true on the boundaries, and so we check some for some real value function. We check some condition, and it's true. And for the left part, we do something similar as for the left part before for our covering. So we wait, we take the point, some small neighborhood, and we wait if we are for the time we are not so small. This p is pi over 6 diameter, 2 times this. It says that we are not so small, and we calculate that it happens. It takes at least four steps with these values. It takes at least 4 steps. Time to be f and 0 here, and then we do the next step. We are not so small, and the next step we are big. But this set, these are the same estimation. It's quite far to the right. It's far compared to the.
So you want to say that passing from z located to the right gives you already a big derivative.
Yes. So the only last step, going from not so small set to third big, gives us the big derivative, and all steps before we have a bounded distortion. So
and because this is a periodic exponential, but k, the number of steps we need to go to the right is very, very small. It's like we can be bounded this lower.
We end up with some estimation f derivative of is bigger than some constant than this value of direction of 0. And we just need to prove that with some simple induction that at the end of the value of zeros and the end duration of zero is a constant is bigger than eta to the n or something like this. But we have that t is at least 4, so we have a base of induction. We calculate it and we are good. But the small issue is that this 1 and 2 follows from the thing that if we are really far to the left, we can be, this block can be so big that we ends up in, okay, so maybe forget it. There is a small small adjustment in the two, and there is 1 and 2 follows. And but there is a problem. And this problem is related to the situation where when E touches the real line. Because if you want to pull back this set, and we pull back with F, at some point, set E touches the negative real line. And this is S, this is some pre-image of S. And we need to do one more step or more step. Then we end up with this strip set like this.
So the question is, when we pull back the covering from the right into this middle part, we have to obviously control the number of these components of the.
So it may double.
It may double. Thankfully, only that.
So even that the size of this set is small, but we need to consider the set as a two parts. This is quite far from each other. So we treat it separately. So we need to be sure how many sets we have at the end. And fortunately, such situation that the image of EK if for them K touches real negative line may happen only once. So our set may double, but it doesn't break our estimation on Hausdorff dimension. And the proof is follows from the definition of escaping time, because in the behavior of the real line, a few more minutes. So I will tell why, but with that we just treat it separately. We pull back into this part and this part separately, and everything is why this is why it happens at most once. So suppose it happens twice. So we have at time p1 smaller than p2, p1 and p2. So this is E p1 with proper upper limits, and this is 0. So it touches real. And we go with iterations of E to the time p2. So by our assumption, E p2 touches the negative real line, but it also touches positive real line because E p1 at time p1 touched the negative real line. So we start with E p1, it touches negative real line. We maps E p1 with F, with P2, P1, and we end up with at least some subset of P2.
Okay.
And
This is the part where it's absolutely crucial that lambda is real.
yes, this is the part where we need to assume that lambda is. And this is the contradiction if we assume something. Up to that moment, M was just big number, but we can assume that M is big and it's some iteration of 0. And with that assumption, points on the negative real line has a different escaping time that points on the positive real line.
Okay.
So this set can touch both of outline because points in this set has common escaping time. So with that, we can do a similar estimation with some geometric series with eta, and we end up with the same. And the inductive, this is almost the end. The inductive part is that we created, if we have Fn minus 1, first we created R1 by the same construction, and having R1, Rn, and having Rn with this construction we created Ln and Mn. So first we have Fn minus 1, then Rn, then Ln and Mn. And with some inductive proof with this estimation we with the theorem. Thank you.
Thank you. Other questions? Yes.
Is it reasonable to consider other notational dimensions for those sets, like packing, box counting, and so on?
So the honest answer is I don't know. I know that there are some people, some are
In the audience?
Do something with other dimension, even I don't know correctly, with some results, but I didn't think about it, so I don't.
Sure. So it's not like for free Hausdorff box is the same or something. It's all for free boxes.
Maybe Parkinson box will be two.
So if I know, as far as I know, it's harder. That's what there's it's like that because he works together with
If you want, you'll hear it next.
What about non-real numbers? Faster stating lambda?
Okay, so for non-real lambdas,
Because as I
there
understood.
are some results about indecomposable continua due to Rempe. No. What about the Hausdorff dimension? Okay, so in this part we directly use the assumption that lambda is real.
But even lambda, any lambda larger than 1/e is not so evident.
Yes. But for some technical
Is it a
reasons, we
technical?
use lambda equals 1. It's not so. I mean, the generalization with this proof it's not so direct, but I believe.
We can definitely prove it
The
for
same
bigger than
proof,
one, but
right?
it's
But if we have some specific value minus 3, and with that values we cannot generalize this for bigger lambda, but I think we can. I mean, this part with dividing middle part into left, middle, and right should be done should be done better, and I think that with that we can generalize it. Because the idea of pulling back is the same for all lambdas, at least bigger than 1/e.
So the optimistic view is we want to try to generalize this into 2πi case. But obviously this technique doesn't work at all for 2πi because we don't have this very nice real line, and so we decided to like stick to the lambda equal to 1. Just skip at least some technical difficulties because only did a lot of technical difficulties we're fighting with the ever-changing itineraries, and there's also some slightly more problems with this counting of the how many actually of those pre-images do we have. So there's enough technical difficulties, so we decided to like omit 1 and stick to lambda equal to 1. But hopefully we have some ideas how to try to do the 2πi.
How long is the paper?
Now about 20 pages.
23, I think it's now or something. I don't remember.
Sorry, I have some. But
You don't know the version, obviously.
not the current version, but
The last page.
okay, here's 19, but I'm sure it's
Okay, so it's 23 or more or less because I've added 3 since you last talked.
Questions? Okay, so let us. Bardzo ciekawe. Można się tego stwierdzenia, bo to jest, że chodzi o to, żeby wyjść z tego warstwa było zdekompozowane.